Good afternoon, everybody. Welcome to our second press conference today here at the 230th AAS meeting in Austin, Texas. I'm Rick Fienberg, AAS press officer, and I'm assisted today by my deputy press officer, Larry Marshall, who's monitoring our online webcast, and by Benny Tsang. Where are you? There you are. He's our Astrobytes media intern. If you don't know what Astrobytes is, look it up. A couple of quick announcements. For the press registrants, please remember to sign up for our press dinner and our press tour, both of which are happening on Wednesday. There's sign-up sheets in the press office, room 404. They're taped to the end of the table nearest my workstation. And then if you're interested tonight, there's a special AAS version of Astronomy on Tap at the North Door, an Austin bar, where three well-known astronomers will be interacting with the public and talking about citizen science, the search for worlds out beyond Pluto, search for Planet 9, and searching for exoplanets. Those will be Jackie Faherty, Konstantin Batygin, who many of you know from Caltech, and Bonnie Meinke. Doors open at 7:30, and the address is on the bulletin board in the press office. Please silence your cell phones if you haven't already. And if you're on the AAS press list, you should have received 4 press releases, 2 for the first story and 1 each for the second and third stories. So in case you haven't been to a AAS press conference before, I will introduce the topic and all of our speakers, and then they will give their presentations in order, and we will hold questions and answers till the end. And when it is time to do Q&A, please wait for a microphone so that the folks on the webcast will be able to hear your question in addition to the speaker's answers. All right, well, as I mentioned this morning, we cannot have a AAS meeting without at least one press conference on exoplanets. And this is the one this week. Hot planets and cool dwarfs, stars, planets and objects like planets that aren't quite stars. We're going to have, we have 3 papers being represented with 4 presenters. The first paper is A Transiting Gas Giant Planet Hotter Than Most Stars. That paper was published online in Nature this morning. That's why you see Nature up on the screen. Nature, Leslie Sage at Nature, as he has done in the past, helped work with us so that we could get that paper online today in time for Scott's science talk this morning and the press conference today. Scott Gaudi from Ohio State University will be opening that presentation, and he'll be assisted by Karen Collins of Vanderbilt University, one of his co-authors. The next presentation will be Clouds and Exoplanet Atmospheres. That'll be from Giovanni Bruno from the Space Telescope Science Institute. And then Trent Dupuy from the University of Texas at Austin, right here, will be talking about the dividing line between stars and brown dwarfs. And here again we had cooperation from one of the journals, the Astrophysical Journal Supplement Series. They agreed to get that paper online today as well. All right, so with that, I will turn it over to Scott.
Thanks, Rick. Welcome. Thanks for coming. Those of you who don't know me, I'm Scott Gaudi. I'm a professor at Ohio State University. I'm speaking on behalf of the Celt collaboration. Karen Collins from Vanderbilt is here with me to help share this, what we find a very exciting discovery with you. I should also mention the other lead author to this paper is Kayvon Stassen from Vanderbilt University. And again, I'm representing the entire Celt collaboration, some of the other members of whom are in this room. And so with that, I'm going to let Karen tell you a little bit about Celt and what we've discovered, and then I'll tell you a little bit about the implications of that.
Let's see. So I'm Karen Collins from Vanderbilt University. I'm a postdoc there. And okay, so let's get started with a little bit of a historical perspective. The first exoplanet surveys using both the Doppler and the transit techniques focused on sun-like stars. Their advantages, they are easier to detect and they're like home. So started there, but more recently the surveys have driven downward toward low-mass red dwarf host. And that's produced some notable successes recently such as the discoveries of the potentially habitable planets around Proxima Centauri and TRAPPIST-1. But pushing upward to higher mass stars, hotter stars remain, our understanding of planets around those stars remains poor, and that's primarily due to how difficult it is to confirm planets around those stars. So our survey is called Celt, the Kilodegree Extremely Little Telescope, and it's an all-sky survey for planets transiting bright stars. You can see a picture of it there. It is low-cost, mostly off-the-shelf technology. Basically, it's a scientific-grade camera with a professional-grade lens attached to the front of it. And there are two of these, one in the southern hemisphere and one in the north. And between those two telescopes, they've produced 20 planet discoveries now. More than half of our target stars are hotter and more massive than our sun. So we have developed techniques for surveying those hot stars. And our collaborators, in particular, Dave Latham's group at the CFA, have developed techniques to help us confirm our planet detections around those stars. So we are very excited today to announce the discovery of Celt 9b. As has already been said, it's a gas giant planet hotter than most stars. And I want to emphasize that's not a typo. It is stars, not hotter than most planets. It's so hot because it's orbiting the brightest, hottest, most massive known transiting gas giant planet host star. And that host star is about 2.5 times as massive as the sun and about 17,500 degrees Fahrenheit, which compared to the sun at about 10,000 degrees, a lot hotter. And it's so rapidly rotating that it's flattened along its polar axis. Sort of like Saturn is, if you see an image of Saturn. The planet itself is the hottest gas giant yet discovered, and Scott will show a plot of that in a bit to show you how much hotter, and it's in a 1.5 day orbital period around the planet, around the star. So the combination of that very close-in orbit and the really hot star produces this super hot planet. The planet itself is about 3 times as massive and 2 times larger than Jupiter. And it's tidally locked, so the same side faces the star for the entire orbit. And the dayside temperature of the planet is nearly 8,000 degrees, so it's only a couple of thousand degrees cooler than the sun itself. And that's so hot that we were able to measure that with modest-sized telescopes from the ground, like half-meter-sized telescopes. And finally, the orbit is pretty interesting because it orbits perpendicular to the equator of its host star. And Scott's got some great demonstrations of the illustrations, so I'll let you take over.
Thank you, Karen. So these aren't my illustrations, but we enlisted the help of the JPL experts to give us a kind of a sense of what the system would look like if we could actually see it with our naked eye. So the star itself would appear blue to our eyes because it puts out most of its light in wavelengths that are at the very blue edge of what we can see, and even a lot of light in the ultraviolet that our eyes can't see. The star rotates on its axis about once a day, a little bit more than that, and so as a result, it's very flattened, and you can see that in this illustration. It would appear just as flattened as Saturn would to our eyes. And the planet, like Karen said, is tidally locked. So its day side is extremely hot, only a few thousand degrees cooler than the sun. So it would appear slightly dimmer than the sun and slightly more orange than the sun, the day side. The night side, we're not really sure, but based on our one measurement of the secondary eclipse depth, we think that the amount of heat that the planet's atmosphere can redistribute from the day side to the night side is probably pretty poor. So the night side probably would look like a red dwarf to our eyes. And finally, because it's emitting like 700 times more ultraviolet radiation, the host star, than any other known transiting giant planet host star, the planet is almost certainly being evaporated by the high energy photons. We don't really have a good estimate of the mass loss rate, but it could be something like 10 billion or even 10 trillion grams per second. So it would likely have a cometary tail, as you would see here. And again, as Karen mentioned, the orbit is very strange because this planet, rather than being orbiting in the plane of the equator of the star, is orbiting perpendicular. It's going over the poles of the star, which likely would produce precession of the orbit, which should be detectable in a few years. And maybe, depending on what the correct amount of that precession, the planet may actually stop transiting in 150 years. We'd have to wait another couple millennia for it to come back again. So other than being an extreme planet, this planet is also going to be a very extreme system. It's going to be a great system for us to study with HST, Spitzer, and eventually James Webb Space Telescope, not to mention ground-based facilities. So this plot is basically showing known transiting planets with measured masses. So hotter planets are to the right, and planets with thicker atmospheres or larger scale heights are up on this axis, on this plot. And so there you can see Celt 9. It sticks out like a sore thumb. The color represents the amount of UV radiation. So like I said, this host star imparts 700 times more UV radiation on its transiting planet than any other known gas giant. So that means it's not only hot, but it's probably evaporating, as I said, very rapidly. And so everything to the top right are things that are easier to characterize with all these facilities that I mentioned. And so we're really looking forward to trying to characterize the properties of this planet and understand it better. So just to summarize, we've discovered the brightest, hottest, most massive known transiting giant planet host. It's a little bit brighter than in the V-band, HD 209-458b. The gas giant itself, the day side, is hotter than any day side or any gas giant whose temperature we've measured. It's on a bizarre 1.5-day orbit that's perpendicular to the equator, and it receives an enormous amount of ultraviolet radiation. It's very puffy, it's very hot, and those properties should make it very easy to characterize along with the very bright host star and with HST, Spitzer, and James Webb. Thank you. Reset? Yes.
All right. Thank you for coming. My name is Giovanni Bruno, and I am a postdoc at the Space Telescope Science Institute in Baltimore. And today I will talk about a work we've been carrying out at the Space Telescope and other institutes. There's a long list of collaborators about the two hot Jupiters, which are very interesting for the understanding of clouds formation in giant planets. First of all, it's probably better to give an idea of what a hot Jupiter is. A hot Jupiter is not a planet like Jupiter. What it has of similar to Jupiter is the mass and the size, but as you can see in this image, the orbit of our own Jupiter is not to scale, but it's much farther than the orbit of the Earth from our Sun. And instead, the orbit of a hot Jupiter is much closer to its star than it is Mercury in our solar system. So as a result, a Jupiter and a hot Jupiter have very diverse properties in terms of temperature, especially. And this is why it's interesting to study the atmospheres of these planets for which we don't have any similar case in our solar system. And in particular, by studying their cloud formation processes, we have a window in the understanding of what's happening in their atmospheres. So this is why we consider these two planets. Again, our understanding today of cloud formation in giant planet atmospheres is based on two parameters. One of them is the temperature of the atmosphere that you see in this graphic on the horizontal axis, and the other one is the surface gravity of the planet. The squares are giant planets that have been you see that for different temperature and surface gravities, we expect different kinds of condensates or clouds, let's say, in their atmospheres. So you have different clouds and images in this plot. And in particular, our two planets are the two black dots in about the center of the image. So we're talking about WASP-67b and HAT-P38b. One of them is the size of Jupiter, the other one is more the size of Saturn, but the interesting thing is that the combination of their mass and radius makes so that they have a surface gravity which is very similar to the one of the Earth for both of them. Also, they orbit on a very similar orbital period, a very similar distance from a very similar star, which means they receive a very close amount of irradiation. And as a result, their temperature is also very similar. It's about 1300 Fahrenheit, which means that in this plot, as you can see in this plot, we expect molecules containing alkali elements in their atmospheres. So the purpose of our study was to see if we consider two planets which have very similar parameters according to our understanding, are we going to see the same clouds or not? So this is how our experiment looked like. We used Hubble, and we observed the transits of these planets in front of their respective stars. Once a planet transits in front of its star, we observe a dimming of the starlight. And so you have two plots, on the left the WASP-67b and on the right HAT-P38b. That's how their transits in the infrared look like. And how do we study the atmosphere of these planets? We measure the transit depth, which is the amount of light which is dimmed by the star. And we measure this thing in different wavelengths. And what we obtain is something like this. So on the top you have the plot, the spectrum for HAT-P38b, and on the bottom for WASP-67b. We're looking in a band which goes between 1.1 and 1.7 microns. And in particular, we're interested in looking at the water absorption peak at 1.4 micron. What you have to take into account is that for planet people doing planet atmospheres, spectra are flipped. So actually, when you see an increasing bump, actually there is an absorption. So what we're seeing here is that there is more absorption, more water absorption for HAT-P38b than for WASP-67b. How do we interpret this? We relate stronger water absorption to a clearer atmosphere, which means an atmosphere which has a lower amount of clouds, and a dimmed water absorption feature with an atmosphere which has either a high altitude cloud deck or a higher metallicity content, meaning a higher amount of elements heavier than helium. So these two plots tell us that the two planets are not as similar as we think they are. And in particular, as the water absorption feature of WASP-67b is less wide than the one for HAT, it means that either there is a higher altitude cloud deck than in the HAT-P atmosphere, or that its atmosphere is more metal rich. To understand why this is the case, we have to go probably to study the formation condition of these planets. So the idea is that hot Jupiters don't form as close as their star as we find them, but they form much farther. And then here you have an image of a hot Jupiter of a giant planet in formation around a star and a protoplanetary disk. And the planet will migrate towards the star. And according to the position where it forms in the disk and the migration history, it will accrete different materials. So probably the answer lies in the history of formation and accretion of these two planets, which, however, for the moment, we cannot yet probe. Because to understand, to distinguish the two cases, we need the abundance mainly of two elements. One is oxygen and one is carbon. The abundance of oxygen is something we can measure with HST by measuring the water absorption peak. But instead, for carbon, we need to go farther in the infrared, and for this, we will need instruments like James Webb, so we need to wait a little bit more. So to summarize, we have two apparently very similar planets which have very similar temperature and surface gravity. So we expected them to have similar kinds of clouds, and so similar spectra, but instead what we found was that one of the two planets is probably cloudier than the other or more metal-rich than the other. So the two planets don't have the same formation history. But to better understand this, we will need future instruments and further studies. Thank you.
All right. Reset. Okay, good, great. So the work I'm presenting here today is the result of a long-term effort spanning more than a decade to better understand the fundamental properties of the lowest mass stars and brown dwarfs using some of the world's most powerful telescopes. So this is a brief outline. I'll start by talking about how mass defines the dividing line between stars and brown dwarfs. Then I'll tell you about our new results that provide the first direct observation of this dividing line that happens to be about 70 times the mass of Jupiter, or 6.7% the mass of the Sun. So mass is probably the single most important property of stars because it dictates how their entire life history will proceed. We really benefit from this on Earth because the Sun's mass makes it shine stably for billions of years, which among other things allowed life to develop and evolve here on Earth. Okay, but not everything in the galaxies is so nice and stable. In the grand scheme of things, the Sun's mass is just right. It's sort of Goldilocks star in that sense. And if it were much more massive, it would burn through its nuclear reactions much faster and die young and possibly violently. If it was less massive, then it wouldn't be able to sustain nuclear fusion at all, and then it would simply cool forever as a brown dwarf. And so it's that boundary at the lower masses that our work has helped us to understand better. The idea that there is a lower mass limit for stars has been around for over 50 years. In the 1960s, astrophysicists first calculated that there must be a mass below which the core of a star does not achieve the temperature and pressure that's needed for hydrogen fusion. Above this mass limit, though, we would expect a simple one-to-one correspondence between mass and the surface temperature. This because it's just set by the perfect balance between gravity of the gas pushing down and the gas pressure pushing out, which is stabilized by the nuclear reactions. Below this mass limit, however, there's nothing to replenish the energy that's constantly being radiated away into space at the surface. And so objects will simply cool. An object of a given mass will simply cool forever. And these are what are called brown dwarfs. Sometimes people call them failed stars. And so what we'd expect then is if you go out and look out in our solar neighborhood and measure and look at masses and surface temperatures of things, you'd see this diagram of mass on the y-axis and surface temperature on the x-axis populated this way. Above the mass limit, you'd see this nice one-to-one correspondence between stars and surface temperature. It's the main sequence. But then below the mass limit, we'd observe a jumble of things. Sometimes objects of the same mass could have very different temperatures. Things of the same temperature could have very different masses. And I deliberately left the bottom right part of this diagram unpopular or sparsely populated because that's where very young brown dwarfs would live, and we just don't have a lot of very young objects in the immediate solar neighborhood. So this is just a cartoon of what we expect. This is what this theory has predicted. What we've been trying to do is make a plot like this with real data. So the thing that we already have good methods for in hand is determining relative surface temperatures of low mass stars and brown dwarfs. It's an extension of the spectral typing system that was developed for stars. The thing that we've been missing are the mass measurements. So measuring things so we can get the measurements we need on the y-axis. So that's the work that I'm talking. That's in our paper. What we do is we use binary systems where we can compute mass simply by measuring the size and the period of an orbit. This equation on here tells you that you use the cube of the size and the square of the period. This is just Kepler's third law. And the plot on the left shows you what some of the data that we actually take look like. What we do is we go back to the telescope year after year, take a picture of the binary each time, and watch it move around. And once we have enough information, we can fit a unique orbit to those measurements. So what makes this hard is that the binary components are so close to each other in the sky that we have to use really sharp images to make these measurements. And so some of the sharpest images in the world come from the Keck Laser Guide Star Adaptive Optics System. That picture there shows you the Keck laser in operation. And it's been providing these really sharp images now for over a decade. And that's really been critical to the success of this long-term project. The one drawback of the adaptive optics imaging is that it only gives you a very tiny field of view. So you zoom in and you can see the binary very sharply, but you can't see anything else around it. And so that's the piece of information we've been missing until now. What we need is the mass ratio in order to break up the total mass that we measure from the Keck data. The ellipses on the left illustrate what one of these orbits might look like. We know that in real life, the two components are orbiting an invisible point in between them. It's called the center of mass. And the amount, how massive each component is, determines how big their orbits are around that center of mass. So the more massive component, in this case, is the red ellipse, so it's a little bit smaller than the blue ellipse, which is the lower mass component. So what we've been added to our Keck mass measurements now is the measurements of these centers of mass. And that's come from the Canada-France-Hawaii telescope. And that's been derived from again, decade-long high-precision position measurements of our binaries, unresolved, but in a wide field where we have hundreds of reference stars with data being taken in the infrared. And so that allows us, that high precision and that very long time baseline allows us to see the small wobble of these binaries against this reference grid. So really, it's these two things, the really sharp imaging from Keck adaptive optics and the high precision position measurements from CFHT that allow us to now know exactly how these binaries are orbiting, not just their whole orbit, but we know where the center of mass is, so we can make animations like the one that's in the center of this slide, where we can predict where these binaries are at any given time now. And so, because we have that information, it's fun to make a movie of them. This is the first frame of a movie where all these binaries in our sample are today, at this moment. And then if I just click on it, they'll start moving. So now we're projecting all their orbits forward in time. And at very high speed. So every 1 second of this movie corresponds to 2 years in real life. And this is this is why it took a decade to do this. These orbits are not moving particularly fast. Most of the binaries you're seeing here have periods of 10 to 30 years. And so this is why it's required a lot of patience. The color of the dots in the movie are related to their surface temperatures based on their spectral types. For scale, the top left binary is moving at has an orbital period of 2.4 years. So in the movie, it orbits once every second or so. And the bottom right binary has the longest period and has a period of about 40 years. It's really the masses that come out of these orbit measurements that have allowed us to do the first empirical determination of this boundary between stars and brown dwarfs. And so this plot shows the results in that same sort of diagram that I showed earlier. Mass is on the y-axis, and the x-axis is our empirical way of determining relative surface temperatures, which is based on spectral types, cool on the left, warm on the right. And just as we expected from theory, we find that objects above a certain mass are always on the warm side of the plot. And then there's a critical mass below which objects of the same mass can have very different temperatures. And this happens at roughly 70 Jupiter masses. So this is the first time that we've directly observed this boundary between stars and brown dwarfs as a function of mass. And so it's finally provided a really nice validation of theory that's been around for over 50 years. Interestingly, the critical mass is a little bit lower than we had expected. For many years, people had assumed the boundary is around 75 Jupiter masses, not 70. And so that brings to mind some interesting implications, potentially a substellar boundary at lower masses. This is a zero-sum game, so if you move the boundary lower, then you have more stars and fewer brown dwarfs. So theoretically, that means that there could be more places for life. More interestingly, are that when you move it lower, then you're talking about lower temperature stars, so more extreme environments for planets to orbit stars. One of the lowest mass, coolest planet hosts we have now is TRAPPIST-1. So the boundary I'm talking about is about 10 times fainter than TRAPPIST-1. The stars at the boundary are so cool that they have silicate clouds, like we heard in the last presentation. So you'd be standing on a planet looking up at your star, and your star would be cloudy, not necessarily your sky. So these are some interesting things. So I'll just wrap up. In summary, mass, single most important property that dictates the whole life history of any object. we finally have a collection of many mass measurements both above and below the dividing line between stars and brown dwarfs. It took us over a decade to complete this, mainly because these binaries are so low mass that they orbit very slowly. And the data that we needed was at the very limits of the capabilities of some of the most powerful telescopes. After all of this, though, our data confirmed this long-held theory that there is a dividing line in mass, and it's about 70 times the mass of Jupiter. Thanks.
Well, thank you all very much for some very interesting new looks at planets and brown dwarfs. We're going to do Q&A now. If you have a question, please raise your hand here in the room and wait for the microphone. Benny will bring it around. Tell us who you are and who you work for and who your question is for. And if you're online, please use the text chat facility to queue up your questions for Larry, who will relay them to us. All right, so we will begin. Do we have questions here in the room? Okay, we'll take one down here from Dirk.
Dirk Lorenzen, German Public Radio. I have a question for Karen and Scott. Do you have any ideas how your weird system has formed?
Are these on? Right?
Yeah.
Okay. Yeah, well, so there are lots of, as Giovanni mentioned, there's lots of theories for how these hot Jupiters form. And some of them involve migration through a disk, some of them involve some sort of violent dynamical interaction with either another star or another planet in the system. The fact that this planet has somehow ended up on a near polar orbit likely suggests it's one of the latter violent dynamical emplacements mechanisms. Interestingly, we have adaptive optics observations from Keck, and we do not see any companion star down to fairly faint magnitudes. That doesn't mean that there isn't a star that's either too close in or another planet that could have done the scattering, but there's no obvious contender for what's usually called the Kozai lid-off mechanism for emplacing the planets in these kinds of bizarre orbits.
Okay. Any other questions here? Okay, down in front. Steve?
Steve Marin, freelance in Harvard University Press. I have one for Scott and then one for Trent. Scott, you showed the evaporating planet. Do you have a lifetime for that? When it'll be gone?
So it's a good question. At the lower end of the mass loss rate of only 10 trillion grams per second, this planet will survive quite healthily through the rest of the main sequence lifetime of its host star, which is another 300 million years. At the upper end of that mass range, I think things start to become more uncertain because there may be feedback processes which cause the mass loss rate to accelerate once the surface gravity of the planet goes down as it starts to lose mass. I would say that I wouldn't want to speculate on whether or not the planet will survive. Probably it will, at least until the star encroaches upon it. But I think there's a lot of theoretical work that needs to be done to address that question.
And for Trent, do you have an uncertainty value on that 70 plus or minus 1? Or?
We don't have an uncertainty value yet. That is the next step. We want to do some detailed modeling of the solar neighborhood, do some population synthesis to figure out, given our sort of 20 measurements above, 20 measurements below, how precisely are we really determining this? Yeah.
I had the same question. Do we have any questions online? We do?
Yes.
Okay.
We have a question from Nancy Atkinson with Universe Today and Seeker.com. A question for Scott or Karen. The press release says they want to observe Celt 9b with space telescopes. What other characteristics or features on this world are they specifically most interested in getting more details about?
Okay. I'll mention two things. I think there are a lot of different things we could try to measure about this system. One is that we could try to get the phase curve of the planet as it orbits its star, and that would tell us the efficiency of heat redistribution on the planet, which is predicted to be pretty poor, which means that the day side should be very hot and the night side should be very cool. The other thing we'd like to do is maybe get transmission spectroscopy, so that's as the planet passes in front. Well, this is what Giovanni was talking about. We could try to do that with this system as well. It's really unclear what we expect there, but it could be that as the day side, the gas gets transferred from the day side to the night side, it cools down enough that molecules can reform. And so you might actually see molecular features at the terminator of the planet, which you might be able to pick up with HST or JWST kind of observations, similar to what Giovanni was talking about.
And then the one other thing that you touched on was the precession.
Right.
And how long that maybe we'll still be able to see the planet transit its star before it goes away for a while and then comes back a few thousand years afterwards, probably.
Okay, we'll come here next, but Larry's got one more from the web.
It's not from the web, it's from myself, Larry Marshall, Deputy Press Officer, for Scott or Karen. I'm just curious, observationally, how did you determine the inclination angle of the orbit? Because that must look rather strange if it's a McLaughlin-Rossiter effect, and also the oblateness of the host star.
So the oblateness of the host star is a theoretical prediction based on its mass and how rapidly rotating it is. It's something we could in principle measure with very high precision light curves, perhaps. And especially if the planet's orbit precesses, then we might be able to measure it that way as well, because the transit duration will change. The other question about the inclination and how we found that it was on a near polar orbit is actually quite amusing, because we tried to get Rossiter-McLaughlin effect measurements, and we saw nothing, at which point we thought it was a false positive. But then we did a little bit, got a few more additional observations, did a fancier analysis, Doppler tomography, where you're actually looking for the shadow of the planet in velocity space. And we found that indeed the planet was pathologically, just to make our lives difficult, going right almost down exactly the spin axis of the star, leading to almost no Rossiter-McLaughlin effect, but a very clear Doppler tomographic signal, which indicated that inclination.
Okay, we have a question down here.
You half answered my question. I was just wondering if through the light curve you could detect the limb brightening profile of the star. That might give you a sooner measurement of any precession changes in the ingress and egress of the light.
Can you identify yourself so that the
Steve
webcast
Lawrence,
folks will know who you
Hofstra
are?
University.
Yeah, so well, there's several effects going on. There's still limb darkening, but there's also gravity darkening because of the oblateness of the star. Those are not detectable with the precisions that we have now. And I think you'd probably require something of the order of tests to be able to do this. My guess is, and I'm actually going to throw this to Marshall Johnson, who's an expert at this. My guess is we can detect the precession sooner with Doppler tomography than with the shape of the light curve. Would that be your guess as well?
Yes, that'd be my guess.
Marshall's going to try to do this, actually.
Any other questions here in the room? Any more online? Okay, I've got a couple. My first one's for Giovanni. You talked about the different metallicities of the clouds in the two planets, right? Some of the clouds may be more
the overall atmosphere.
metallic, right? So the question is do you have any indication from the properties of the host stars whether whether alkali metal type clouds or a different height of the cloud deck is more likely? Is there anything about the metallicities of the stars that's sufficiently different?
That's a very good question, and I'm not sure I can answer 100%, but as far as I know, there should be, people look for a relationship between the metallicity of the star and the one of the atmosphere of the planet, but until now, we don't know.
Okay.
So, maybe.
Okay. And then a question for Trent. What was the scale bar in like arc seconds for those animations of the systems? Are we looking at objects that are within an arc second of each other, or how challenging an observation is it?
Right. So the movie that I showed actually was because we have parallax distances to all of them. So I put them as if we were viewing them all at the same distance, and so the widest orbit at the very bottom was sort of 6 AU. Now, typically for the binary semi-major axes are roughly 0.1 arc seconds. So that's their maximum extent. So to do the orbit measurements, we have to track them wherever they're at in their orbit. So we have to go inside 0.1 arc seconds. So most of our measurements are, we do within 0.05 arc seconds, and then some of them go down to 0.03 with, we use non-redundant aperture masking at Keck for some of that. Interferometry techniques to go as tight as possible.
Have you been able to follow any of the systems with Hubble, which can give you that kind of resolution without having to do adaptive optics?
So yeah, so a couple of systems we have followed with Hubble because the laser guide star system at Keck is very good at providing a correction for almost everywhere in the sky, but it still needs a relatively faint star to lock onto to correct for the first order terms of the turbulence in the atmosphere. And so it doesn't actually do the whole sky. And so there's a few really interesting brown dwarf binaries that we couldn't do. So we did those couple with Hubble. Otherwise, it would be a really expensive Hubble program to try and hit all of these consistently over 10 years. It's not really, it's something that's very well suited from Keck, but not so well suited to Hubble. But we did do that with Hubble. In principle, the aperture masking at Keck is competitive or better than some of the even optical imaging with HST.
Okay. Very good. One last chance for any questions either here in the room or online. Larry, anything? Nope. Everybody's just kind of laid back. It's because we're in Austin. Yeah, all right. Everybody wants to hit the bars and go with the music. All right. Well, thank you all very, very much for these very interesting presentations. Exoplanets continue to be mind-boggling. I should note, just because it's kind of interesting, that this is the first exoplanet briefing I can think of in a while that didn't involve any Kepler results. It's not because Kepler isn't still doing good work, it's just that they didn't happen to have anything to present at this meeting, in part because they had their own science meeting also this month. But of course, we're now within a year or so of beginning to get data from the next exoplanet satellite, which will again open the whole field up to all kinds of interesting new things. So keep your eye on exoplanets. We have another briefing tomorrow morning at 10:15. That's on inconstant stars, variable stars of different types, and again tomorrow afternoon, and again Wednesday morning. So we hope we'll see you again here at 10:15 Central Time tomorrow morning. And that's it for today. Thanks very much. It's all right. If you want to clap, you can clap.
Yeah, it's so weird to talk and not have a clap.
It's neither mandatory nor
And like not clap yourself.
prohibited.
After Scott goes on.